For today's algorithm, we're going to be discussing binary trees and their counterpart, binary search trees. So a binary tree is a tree data structure in which each node has at most 2 children. A binary tree has a root, a left subtree, and a right subtree. The leaves of a binary tree are the bottommost nodes of the tree, and a path in a binary tree is any sequence of edges from one node to another. So each node in a binary tree has the following fields. Each node has a right child. In our example on the left, the right child of A is C. Each node also has a left child. The left child of A is B. Now, the right and left children can be either a node or null. So in this example, the right child of D is null. And the left child of E is null. Every node in a binary tree also has a data field or a key. In our case, the keys or data fields are the letters inside of each node. And in some trees, you'll find that they have parent pointers. In this example, the parent of B is the root A. And the parent of the root A is null. You know you are at the root if your parent is null. So now that we've defined what it is a binary tree, we can now discuss binary search trees. So a binary search tree, or BST for short, is a sorted binary tree that maintains the binary search tree property, which keeps its keys in sorted order and allows for use of the principle of binary search for its operations. Now you might be asking, well, what is the binary search tree property, or the BST property? Well, the BST property is the property that defines that every node in the tree has a right subtree for which each node in that subtree is larger than the current node. And each node has a left subtree for which each node in the left subtree is smaller than the current node. So, for example, let's take a look at a tree with a root 50, left subtree containing the node 30, and a right subtree containing the node 60 as its root. So since 30 is less than 50, we know that the left side of this tree maintains the binary search tree property. And since 60 is greater than 50, we know that the right side of this tree maintains the binary search tree property. So we can safely say that this is a binary search tree. One thing you will notice is that we can use the binary search tree property to infer where a node will be based on the key of that node. So if I were to tell you that 35 existed within this tree, we would know exactly where 35 would exist if it were there. So how do we tell? We first look at the root, and we notice that 35 is less than the root. So we know 35 must exist in the left subtree of 50. And we also notice that the root of the left subtree, 30, is smaller than 35. So 35 must exist in the right subtree of 30. However, at this point, we also notice that 30 is a leaf. And since 30 is a leaf, we know that 35 exists to the right of 30. Now let's take another example. Consider the root 70 were in the tree. Where would it be placed? Well, 70 is greater than 50, so we know it must be in the right subtree of 50. And 70 is also greater than 60, a leaf node. So we know that 70 is the right child of 60. Now let's take a look at a second example. Consider the tree rooted at 30. with a left child 25 and a right child 50, whose right child 50 has a left child 5. So let's decide whether or not this tree maintains the binary search tree property. Well, let's take a look at 50 first. Every node of 50, every node in the left subtree of 50 needs to be smaller than 50. Well, the only node in the left subtree of 50 is 5, so that does maintain the binary search tree property. And there are no nodes in the right subtree, so that also maintains the binary search tree property. Now let's take a look at 30. Every node in the left subtree of 30 must be smaller than 30, so the left subtree of 30 contains only 25, so this maintains the binary search tree property. And every node in the right subtree of 30 must be greater than 30. So in the right subtree of 30, we have 50, which is perfectly fine. That maintains the binary search tree property. But in the right subtree of 30, we also have 5. Now 5 is less than 30, but exists in the right subtree. Therefore, we know that this is not a binary search tree. In addition, we actually can find out where 5 should exist in this binary search tree using the definition of a BST property. So we take a look at the root. We notice that 5 is less than 30, so it has to be in the left subtree. And we realize that 5 is also less than 25, so it must be in the left subtree of that. And since 25 is a leaf, we know that 5 must be the left child of 25. Thanks for watching our tutorial on binary trees and binary search trees. Stay tuned for our next video, which will discuss binary search tree algorithms such as search, deletion, insertion, min, max, display, AVL, everything you need to know. Make sure to like, comment, subscribe, show some respect in the comments, and stay tuned for our next video.